Welcome to the 2025 fall semester SAFL Student Award Ceremony. Okay. My name is Lian Shen. I'm the director of St. Anthony Falls Laboratory. Okay. And well, this day is always one of the most wonderful day for me on this job is because I'm going to join you to celebrate the success of our students. And today we are going to celebrate the AUNT Award, Student Award. You are going to know it very soon. And also Silberman Fellowship awardees, and also Anderson Award. Okay. And so we are going to have a very wonderful program, and we are going to hear advisors introducing the students who got the award. And before that, we are going to hear about the remarks about Professor Roger Arndt and Professor Silberman and also Professor Anderson. And they are all former directors of the lab. Yeah. And of course, okay, then okay, those awardees, they are going to give a short presentation about their research. Okay, and then okay, feel free to ask them questions to see. Okay, well, yeah. Okay, yeah. Well, let me first start with the first award we are going to present. And I have the honor to introduce Professor Roger Arndt. Okay, yeah. And Professor Arndt is a former director of St. Anthony Falls Laboratory. And he came to the University of Minnesota in 1977, okay, as a professor in the Department of CEGE, but actually it was not called CEGE at that time. It was called the Department of Civil and Mineral Engineering at that time. Okay, yeah, okay. And and he also was named the director of St. Anthony's Laboratory. Okay? And before that, he was at on the faculty of Penn State University, and before that, he earned his PhD at MIT. Okay. By the way, Professor Arndt, okay, was the third winner, okay, of the Straub Award. Okay. So for those of you who haven't done that yet, well, not now, okay? After the ceremony, go to the room next door, look at all the pictures on the wall, look for the third picture, okay? That is, yeah, okay. So Professor Arndt is the third Straub Award winner, okay? And then after MIT, then he went to Penn State, and he became a faculty member in aerospace engineering, right? Is it? And a student in aerospace department there taught him how to fly airplane. And he had, after that, for many, many years, he flew the airplanes to go to conferences and went to a business trip. Okay, yeah. And there, I heard a lot of stories about how he grabbed colleagues or students to fly with him to go to conferences. Yeah, okay. And well, okay, your current director must be disappointing, not want to do things like that to you. Okay, yeah, okay. Yeah, okay. And then after the several director's job, and Professor Arndt went to NSF, and he was a program manager, program director of the fluid dynamics program for several years. So therefore, Professor Arndt also made a huge impact to the fluid mechanics community across the country for that. And Professor Arndt is a top expert in hydroacoustics, turbine machinery, and cavitations, and hydropower. Yeah. So his research footprint, you can see that all over the place. Yeah. And well, as I mentioned, Professor Arndt liked flying airplanes. He super liked traveling. And then on one of his trips, he met his wife, Jane Arndt. And they met in Australia, right? And ever since, Jane has been an important part of Professor Arndt, and she has been so supportive of Professor Arndt in his research and also his interactions with the lab. Okay, so thank you for your super strong support to the SAFL students, generations after generations of students. Yeah, really. And one last thing I want to mention is, well, this past February 14th, Valentine's Day, when my wife and I went to a restaurant, then we ran into Roger and Jane in the same restaurant, and Jane's called it a double date. All right, okay, well, without much ado, okay, then, okay, I am going to invite the student winners advisor to come up to the podium to introduce the student, Professor Judy.
Thank you, Lian. Hello, everyone. I'm Judy Yang. I'm a faculty in CEGE, and it's my great pleasure to introduce my student, Yuan Li, to receive Roger Aunt Award in front of the Roger Aunt family. So thank you very much. And Yuan is currently 5th year graduate student in CEGE. She joined my lab about 4 years ago. Before she joined my lab, she was doing simulation for her master's degree in China, University of Petroleum. So she started a new research direction in experimental fluid mechanics, learned how to grow microbes in algae, and led 4 research projects. And more remarkably, those 4 projects all use different methods. So Yuan was a quick learner, was able to master all the technology and skills. She published 2 papers, and the third one is accepted recently, and she has 4th paper going to submit soon. So I'm very proud of her. And Yuan previously received Heinz Stefan Award, right? And she also received the Best Oral Student Presentation Award in the National Harmful Algae Conference. What's more remarkable is her research on developed a novel material to remove harmful algae. And that set up us for a new big grant from Army Corps of Engineering, which was $2 million, basically to apply her method in the field. Actually, this morning I received an email from companies saying they are testing Yuan's method in the field. So, and in addition, Yuan also did a lot of outreach. So she designed hands-on activity and shared her story with over 100 K-12 students. Well, I can go on and on, but I know my time's limited, so I'll let Yuan present her research. And she will defend her thesis in December. So if you want to hear more, come to her thesis.
Oh, thank you. Thank you for Julie's introduction. And I'm very honored to have this fellowship. And thank you for Professor Roger. And yeah, I'm Yuan, and I'm almost done my PhD. Yeah, so let me just like give you a review of what I have done in these 4.5 years in SAFL. It's about the removal of harmful algal cells and toxins through clay algae flocculation. So thank you, Professor Roger, and again, and yeah, I think Lian have gave a good introduction to the Professor Roger, but I have to say thank you for this fellowship and to help and assist a lot of students to do what they want to do and to doing research in SAFL. So first, let's give you some introduction of harmful algal bloom. So harmful algal, I think everyone live in Minneapolis is familiar with harmful algal bloom. Is I mean, Europhonemia in summer in lakes. It's excessive growth of the algae cells in lakes. It's so it can cause a lot of economy and fishes died, and so we have spend a lot of monies in summer to control the harmful algal bloom. So my research is focused on using the clay to control the harmful algal bloom. So actually, in China and South Korea, a lot of research have done that. But my research is first to introducing the transparent clay lignite to control the harmful algal bloom. So there are 3 topics in my research. The first one is we compare the cell removal efficiency among the lignite and 2 traditional used clay, kaolinite and bentonite. And the second one is we introduce turbulence inference on that. We want to say the flocculation under turbulence, is there, does that have the impact on the flocks? And the third one is we done research on the clay absorption on the microcystin, the cyanotoxin, under the different pH, different salinity to see the absorption of the lignite. Yes, here are the videos to showing the flocculation phenomenon under the lignite, bentonite, and kaolinite. So what we can say, after we introduce clay into the alga cultures, we can see the flocculations and the upper water become clean and with the sediment settle to the bottom. We need to be clear about that. So for the lignite, the clay concentration is from 0.2 to 2 gram per liter, and for the bentonite and kaolinite, the maximum concentrations up to 5 gram per liter. So here we confirm that yes, clay can help us to remove the half-alga bloom from the water body. And next, we plot the removal efficiency and its corresponding clay concentrations among these 3 types of clay. And we can say, like, to reach the 80% removal efficiency, the optimum concentrations for the lignite is only 0.05 gram per liter, and for bentonite and kaolinite, they are 2 gram per liter and 4 gram per liter. So which means like using the lignite is about the 40 times or 60 times less than to using the bentonite and kaolinite. And we look into that, we want to say what causes superior performance about lignite. We investigate the data potential and the particle size, and we think the smaller particle size is a major reason to cause lignite's superior performance, because the smaller particle size means you can have the higher encounter rate and to get the higher cell removal efficiency. And my second project on half-alga bloom is to using the turbulence inference to introduce turbulence. Since in our lab conditions, we're using the clay and alga cells mixing wheel culture, and in the still conditions to see the removal efficiency. But you know, in the field, in the lakes and rivers, a lot of reasons can cause a fluid motion, like the wind or the temperature variations. They can introduce turbulence in the lakes. And another question is, if I spray the clay suspension in the lakes, we cannot mix them well to create the uniform distribution conditions. So we're using this plankton tower with oscillating grid to generate turbulence inside it and to see the remote efficiency under turbulence. So here we can say the remote efficiency have increased after we introduced turbulence in that, which is a good news for our field application. And we also to take a lot of image under different conditions to see the flux change, and we analyze the settling velocity and aggregate size of the flux and to calculate the densities, and we can see the result suggests that the turbulence can increase turbulence can increase settling velocity and aggregate size in general. And the third project is about the microcystin, the toxin. This is why we called it half-alga bloom, since it can the alga cells sometimes they can produce in the toxin in the water, and which is harmful. So we investigate the lignite and bentonite and kaolinite absorption to the microcystin in lab conditions to say which one perform better. And we can say in the left figure, the lignite shows superior absorption performance compared to the bentonite and kaolinite under different toxin concentrations. And we also compare the absorption under different pH and different salinity. We know in lakes, the salinity is pretty low, but in the marine conditions, the salinity can reach 35 ppt. And for the pH, since the half-alga bloom can increase the pH of the lakes, we also do the research on that. So we found the absorption of microcystin to clay prefer to low pH and calcium-enriched environment. So these are the third topics on the half-alga bloom project, and I have also done the research on the bacterial counterflow and the one field investigations of using LabNet to remove alga bloom in the stone lab. And finally, a lot of thanks to Judy and my group members' help, and thanks to the fundings to support my research. Yeah, thank you. And finally, I will have my final defense on December 11th. So if you have any interest, welcome. Yeah.
And so we are moving on to the next award. Okay, that is Silberman Fellowship. And I want to mention, and actually today we have a family member from Silberman family here. Okay, and so let's welcome her. And yes, also thank you very much for the support. Yeah. So I'm going to invite Professor Peter Kang up to give an introduction about the Silberman Fellowship.
Thank you, everyone, for being here. I think this is really important moment to celebrate our student success, which means the success of SAFL. My name is Peter Kang. I'm an associate professor in the Department of Earth and Environmental Sciences. And I'm here to introduce the Edward Silberman Fellowship and also to introduce one of the awardee. So the Silberman Fellowship was founded by the family of Professor Edward Silberman in honor of their father's accomplishment at SAFL. So Professor Silberman joined SAFL in 1946, made a lot of contributions, and he became the director of the lab in 1963, made really lasting impact, and retired in 1981 as emeritus professor. I would say, from my brief knowledge, he really put a lot of effort in laying the foundation of the academic excellence of the SAFL, which has been impacting to this day. So our today's academic excellence of SAFL, I think, is definitely coming from his contribution to the lab. So regarding his research contribution, his field is fluid mechanics. He made lasting impact in many areas, including cavitation, boundary layers, and also water resources engineering in general. The fellowship is intended to support and honor graduate students who not only made academic excellence, but also who has been contributing positively to the SAFL community. And it is my great pleasure to introduce one of today's recipients, who is Jingshan Dong, who is PhD student in my research group. And I think he really deserves to be one of the recipients of this fellowship because she not only made academic contribution to her field of research, but also she's really a caring person who really tried to contribute positively to the community that Jingshan belongs to. So briefly about Jingshan's research, Jingshan is combining mostly numerical modeling and machine learning to better understand transport processes in the subsurface, beneath our feet, basically. And her research is trying to contribute to the better management of groundwater resources and also better management of carbon for climate mitigation. So I think you will hear more about that from Jingshan. And as a faculty, I will say the best blessing is having an excellent student, and Jingshan is definitely a student who makes me feel blessed. So it's been a great pleasure to see her grow as a great researcher, but also a great person. So Jingshan really feels strongly the part of the community, not only as a lab member, but also my lab member, but also as part of the SAFL community. So Jingshan has been actively coming to SAFL seminars and also joining SAFL related activities. So yeah, with all that, I think it's now time for me to present the award to Jingshan and have her talk a little bit about her research.
Yeah, thanks, Peter, for the nice introduction, and thanks the SAFL community for committee for selecting me for this award. Yeah, I really feel very honored. Last year, I was sitting there as an audience and listened to last year's recipient listen to their speak, and I can't help imagine how my advisor would introduce me someday, and who I would like to thank if I got this opportunity to stand here. And this year I'm standing here right now as one of the recipients of the Edward Superman Fellowship. I truly feel like a dream come true. Yeah, this is actually the first award speech of my life, so it's really meaningful and memorable to me. I'm especially grateful to the family of Professor Edward Superman, who established this fellowship. I learned that this was a birthday gift to honor Professor Superman's lasting contribution to SAFL. So this really touched me and remind me of my own parents and my family who selflessly, continuously support me and give me a lot of love. So I think this fellowship not only make me feel more financially more secure, but also like enable me to do something in return to my parents, to thank them their support and also share this happiness with them. Yeah. So with remaining time, I would like to briefly share about my research and what I've been interested in. The research question that I'm interested in pursuing is how the solutes, like dissolved chemical or just tracer, move through the subsurface. Modeling this transport behavior is challenging because the subsurface is geometrically complex. Depending on the scale we are interested in and the rock type, the subsurface could varies a lot. Some media like soil or sandstone has relatively uniform pore structure or uniform or even pore structure. We call this homogeneous system. On the other hand, like in some other system, like sand limestone or a fracture system, the pore structure are more irregular. We call such a heterogeneous system. Heterogeneity is one of the controlling factor that control how solute moves in the subsurface. In the homogeneous system, transport is easier to describe because we see from the particle movie that this particle are moving with average space and in a general same direction. So it's easier to describe. We call such transport Ficant transport. It's easier to describe using a simple law like advection diffusion equation. On the other hand, in a relatively more heterogeneous system, transport with the particle moving with every particle has its own trajectory, and maybe I should play this video again. Yeah, every particle has its own trajectory and with moving with different speeds. So such transport behavior require different methods, the modeling method that can describe this complex behavior. Yeah, and while transport in homogeneous system is well understood and predictable, our understanding of the transport behavior in heterogeneous system is limited. And in the nature, most of the subsurface environment are actually very heterogeneous. So that's brings us to to study the transport in heterogeneous system. And what makes it even more interesting is that the geometry in the subsurface is non-static. It's evolving over time. For example, when the fluid moves through the subsurface, it can react with the rocks or with the median chemically, and as a result, change the pore structure or the geometric structure of the pore space, and this has huge impact on the transport behavior. For example, one example is the mineral dissolution. Depending on how fast the fluid moves and how quickly the rock dissolve, it can sometimes the geometry can change uniformly, so the acidic fluid can make the pore structure smoother, more uniform, and some other times it can form this thick wormhole channels that's making the pore structure more irregular. We call this uniform and wormholing dissolution. So my research focused on how these different kinds of dissolution process alter the pore structure and then change the solute transport behavior. To study this, we conduct simulation using pore network model. In this model, we represent the pore space in the subsurface as an interconnected network. In our system, in the simulation, we injected acid fluids from the left side with a constant flux and inlet concentration, and the pore diameter, as the fluid injected, the pore diameter will increase proportional to the local mineral consumption, which depends on the inlet concentration of the fluid and also the pore diameter of the tube. Yeah. The modeling procedure works in 2 steps. So we first solve the flow. We first run the flow and dissolution simulation to capture the pore space evolution, and then we freeze the geometry and run passive tracer transport simulation to see how the geometry evolution change the transport behavior. In this talk, I will show you 2 scenarios. One scenario is wormholing dissolution in a homogeneous network, and the second scenario is uniform dissolution in a heterogeneous network to see how this dissolution in these 2 regimes change the transport behavior. In the first scenario, dissolution enhance the media's heterogeneity. We see from the diameter field before and after dissolution, and we see after dissolution this fat wormhole formed. I won't be able to go too much detail about the mechanism behind this, but here I would like to highlight is that after the dissolution, the diameter distribution of the system become broader, and this has directly impact the transport behavior. So for the transport behavior before dissolution, the transport is fecal. We see that the particles are, sorry about the videos, the particles are moving with an average speed, and their behavior they're moving more or less at a similar speed. However, after dissolution, we see particle now the particle transport are now more anomalous. They are travel with different speeds, and depending on which part of the system they are entering, their speeds are vary a lot. And to better characterize this difference between the behavior, we use solute breakthrough curve, which is a probability density distribution of the particle breakthrough time at the outlet. And we can see that how the mineral dissolution has dramatically changed the shape of the breakthrough curve. And it's worth mentioning that after the dissolution, the breakthrough curve in red color shows early arrival and then this power law tailing. So the early arrival, the power law tailing is because of the particle that entered into the unreactive zone where the pore diameter are small, and the early arrival is due to the particle entering the wormhole where this thick channel where the velocity and flow is highest. In the second scenario, dissolution homogenized network heterogeneity. Now in the diameter field distribution before and after, or diameter field map before and after dissolution, we see after dissolution, the pore structure become more uniform, and the distribution, diameter distribution now become, after dissolution become narrower. For transport behavior, we see before particles are moving with different speeds. This is very anomalous transport behavior, but after dissolution, the particle now become fecant. They are moving with similar speed. And in the breakthrough curve, we also see that the shape change from curve with a long parallel tail to a shape with inverse Gaussian. So the key takeaway of this study is that dissolution regime has distinctive impact on the transport behaviors. So in the first scenario, in wormholing regime, dissolution, because of the formation of this wormhole and the stagnation zone, we see the transport transition from fecant to non-fecant. So from a predictable behavior to a more complex behavior. And in the second scenario, in uniform regime, we see the transport behavior transition from the other way around, from non-fecant to fecant. And this is because this uniform dissolution homogenizes the network and make it the transport behavior more easier to predict. This study is my first paper, and it was been published earlier this year in the GRL. So if you would like to know more detail, feel free to ask any question or check the paper. Yeah, thank you very much.
And this year we have 2 Silberman Fellowship winners. And now I'm inviting Professor Judy Yang to introduce the second winner.
I'm very fortunate to have so many great students in my group that I have to, because of them, I have to come multiple times today. Yeah, so I'm here. I'm very glad to introduce William Guanju Wei, who is a 5th-year graduate student in CEGE. He also joined my group at the same time as Yuan, and he started from zero with no background in microbiology and learned everything from zero. Now he's a microfluidics and microbiology person in my group. He has led 4 research projects so far. 3 of them has already been published in high-impact papers, and today he will only present the 4th project. And he has been recognized by many awards, including Heinz Stefan Award and Outstanding AGU Student Presentation Award. And he will also graduate in December, so please come to his defense. William has also been a very great member, not only to my group, but also to SAFL. He has been involved in the SAFL student committee and also was helping with the seminar last year. He also helped a lot of outreach events. And yeah, I'm just very proud of you, William, and I know he's always determined to be a professor in the future, so I'm very hopeful that you'll become Professor Wei in a few years. So William, without further ado, I'll give the floor to you.
So let me, as this year's recipients of this Edward Silberman Fellowship. Before I start, I want to I talk about my research, I want to express my great thanks to the Professor Edward Silberman's family for establishing this fellowship. His pioneering work to fluid mechanics and water resource still inspires our work for now. I remember I have a teaching assistant job this semester. We still use the movie, it's very old movie made by Professor Edward Silberman to the student to introduce the boundary layer. Even though it's a very old movie, but it's very, very dedicated, very, very good to show the student how the boundary layer. And this fellowship also encourages and enables me to complete my PhD and give me much confidence about my work. So it's a great honor for me to receive this fellowship. And for my, can I use the pointer? Okay. About my research, I spent past 5 years here working with Professor Judy Yang. We study this interaction between the biofilms, force and particle transport. The biofilms, they are aggregates of cell with some polysaccharides. They are sticky layers. They can form on any surface, like in the drinking water system, like even in our human arteries. They are very harmful, but some biofilms, they are beneficial to some engineer problems. To study these biofilms as they are aggregates of bacteria that are very small, so we need some like visualization system to see the biofilm. So we build up this very powerful visualization system. We have a confocal microscope, the high-speed camera, and the key part is we use microfluidic channels. They are very small, tiny channels. The depth is like to several microns, and we put this macro channel under microscope so we can see how the bacteria grow the biofilms. And we use both experiments, simulation, and the fluid mechanics theory to explain our results. I have done a lot of work during my past years, like to study how the biofilm affects sediment transport, how they grow inside porous medium. But today I will only show one of my current work is we study how the biofilm affects the microplastic transport. This is also my favorite work here. So about this work is we have a straight microfluidic channel. It's a straight channel, like no other geometry on the boundaries. And here we have two inlets, one inlet and another inlet. For the first, the experiment procedure is that we first inject the microplastic beads into the macro channel. This microplastic beads, the density is a little bit higher than the water. So finally, they will settle down to the channel bottom. And after that, we will increase, we will inject the bacterial solution inside the macro channel. The interesting is that we find that when we continue to inject the bacterial cell to the microplastic beads, we find the cells will form biofilms or bioaggregates we call, like at the downstream side of the beads. And finally, these beads will start to move. You can see in this video, like at this part, there will form some bioaggregates, and finally, this beads will start to move. For the without biofilm cases that we didn't see this beads movement and under the same flow conditions. And we do some quantification. We calculate the percentage of the transported beads and also the biofilm area as function of time. And we found that looks as the beads will start to move at the same time when the biofilm area reach a critical value. And from here, we identify the critical biofilm area ratio is about 0.5. Means that in this case, we need about half of the biofilm area compared to the beads area to make the beads to start move. And we also do some numerical simulation, but only for the flow part, to get the reason why the biofilm forms at the downstream of the particle is that because there will be a secondary recirculation region that they can convert the cells and finally make the cells to form the biofilm as particular locations. Also, we do some simulation to calculate some force around the beads and the biofilms. We make this biofilm structure as a very simple structure like this structure. And we do some flow field simulation. We found that when the beads have a biofilm structure, it can generate locally high and low pressure regions. So in this way, it will have additional lead force. But for the abiotic beads, when there are no biofilms, the pressure distribution will be very uniform. And for the with biofilm case, it can increase the lead force to about 17 times compared to with our biofilm case. So in this way, we think why the biofilm makes the reason for the biofilm to make the beads to move is that because the biofilm structure, it can give it additional lead force finally to make the beads to move. The general conclusion for this work is that we find the biofilm growth, they can enhance microplastic transport, and we also identify a critical biofilm area about 0.5. And we find that the reason why the beads start to move is because the biofilms, they will have another lead force to make the beads to move. And finally, I want to thank Dr. Silberman's family again for supporting the students in SAFL, and thanks my advisors, thanks the selecting committee members, and also this funding agencies. Thank you.
Now we are moving to the third part of the program, and that is for Alvin Anderson Award. Okay, and I'm going to invite Dr. Andy Erickson to come up to introduce the award.
Very good. Thank you so much. Good afternoon. Great to see you all. Again, my name is Andy Erickson. I was invited to come up and give an introduction for the Anderson Award. I, as you might expect, am too young to have any overlap with Dr. Alvin Anderson, so I asked my advisor, Emeritus Professor John Gulliver, to give any insights he had, because he did overlap with Dr. Anderson. And he shared a retrospective that I'm going to share. I have it printed because I don't want to miss any words. And so I'm going to use his words primarily, but I have some of my own at the end. So Dr. Alvin G. Anderson's academic specialty was sediment transport, as you can read in the program. And he was well known in the field. However, he didn't try to develop another bed load formula because there were many at the time. He instead decided to work on river meanders, which was an undeveloped area of research, but both important on engineering and geologic timescales. He developed many of the theories that we take for granted today, and with his student, Dr. Gary Parker, moved this field from observational into theoretical. Made a huge impact in sediment transport. Dr. Anderson's PhD research was on air entrainment on the surface of spillways. Because if you remember or knew, maybe you didn't know, Dr. Straub, the founding director, said if you were going to get a PhD, you couldn't do the PhD on funded research. You had to have a different topic. So while he was doing sediment transport, eventually, his PhD research was on aeration. And his in air entrainment and surface of spillways actually resulted in an award-winning paper, Self-Aerated Flow in Open Channels. It used both theory and a very large number of almost full-scale experiments and is the basis for all air entrainment work done today. In fact, the data in that paper has been reanalyzed by at least 2 other investigators, and there has never been a set of air entrainment data to compare to Alvin's. Now, in John's own words specifically, I knew Alvin Anderson only as a graduate student. Alvin left us at the beginning of my second year of graduate school. However, I remember 2 things about him. Number 1, he was an excellent teacher. I had him for open channel flow, and he knew what we needed, and how to deliver it. Number two, I encountered him in the coffee break room late one afternoon, and he asked me what I was working on, with an interest that I knew was genuine. In those days, it was unusual for a professor to show such interest in what a new graduate student was working on. But that was Alvin Anderson's ability to relate to people. So the evidence is that Dr. Alvin G. Anderson had the innovative character to enter an undeveloped field, the endurance to finish a tremendous set of experiments for his PhD thesis, and the interpersonal characteristics to inspire young graduate students. After his untimely passing, the community came together to establish this award, and they felt because they felt a tremendous need to honor Alvin G. Anderson. Now, in my own personal words, as an Anderson Award winner, I hope that this reflection on Dr. Anderson's not only academic excellence, but his relational skills inspires us all, especially the students and the award winners, to live up to the higher standard that he left for us. So with that, I'll say thank you and congratulations to the winners.
Thank you, Andy. And also thanks to John for the nice introduction words. Now I'm going to ask Professor Judy Yan to come up for the last time today to introduce the student winner.
Well, thank you for the very inspiring stories, Andy. I appreciate it. And it's my great honor to introduce my student, Isang, that I study sediment transport. And Isang, standard example to follow. So Isang actually joined my group in January 2025, so in less than a year. I actually gave Isang an offer 2.5 years ago, but I waited for 1.5 years for him to get a visa. But it's totally worth waiting because he is amazing, and he has, in less than a year, he has done amazing job. He proved how salt can make sediment liquefy and affect sediment transport, and already published a paper in the top journal Water Resources Research as the first author. And he also co-authored a paper who is currently in preparation as a co-first author and is currently leading another 2 very impactful research. So I'm just very impressed by your curiosity and your ability to see things, observe things, and I think you have a lot of potential, and I'm just very looking forward to see how much you can grow in the next few years. And I have to say, I secretly wish you will pursue academic career and become faculty in the future, and no pressure, Isang. So without further ado, I would like to invite you to the stage.
Thank you very much, Judy, for a nice introduction. First of all, I want to thank my advisor, Dr. Judy Yang. She is a great person, beside a great scientist. She helped me a lot. She's very supportive. Thank you very much. Also, I want to thank SAFL staff, especially Ben. I bother him a lot during a couple of months, but yeah, I'm not the only one. So also I want to thank the award committee for this opportunity and this award. Also, most importantly, I want to thank our donors, our founders, everyone contributes somehow to these awards. It means a lot for me personally, and I believe that it's very helpful for graduate students, especially international students, financially and also motivationally. So yeah, thank you. A special thanks to Dr. Alvin Anderson and his family for this award. He was a former director of the St. Anthony Fall Laboratory and associate head of Department of Civil and Mineral Engineering at the University of Minnesota. And thank you, Andy, for a nice introduction. I'm going to talk about the erosion of the cohesive sediments and effect of the salinity and organic matters on them. So let's start with the short introduction on cohesive sediments. What are they, how they differ, and why they matter? So cohesive sediments are fine particles smaller than 63 microns, mostly and mainly clay, mixed with organic matters. And interesting point is as little as 15% clay can make the bed cohesion dominant and control the erosion. How they differ, they are not like non-cohesive sediments. They're not that much, their erosion is not that much rely on sand size and like their grain size and density. In the nature, they're mostly held together by electrochemical bond between the clay particles and biological bond from the EPS and biofilm. And this difference in bonding can lead to different erosion mechanism and bed form formation. They're very important in coastal stability. A well-known example can be Louisiana coast, which lost about 5,000 square kilometers of wetlands between 1932 and 2016. And once these fine particles erode, they can affect the water quality, they can increase the turbidity of the water and transport contaminants and pollutants. So the key parameter here for corrosive sediments can be their erosion and critical bed shear stress. And because of the bonding that I mentioned, we expect that salt and organic matter can affect their critical shear stress of corrosive sediments and actually control them. So first, how salt can control the critical shear stress. So basically, clay particles have a negative surface charge, and they're surrounded by electrical double layer. Once we increase the salinity, ions of the salts neutralize the charge, and this electrical double layer compress to each other. And as a result, we have an aggregate and flocculate, and all these clay particles packed tight together, and it can weaken the structure. And this also is very important in nature. Actually, wetlands experience 0 to 35 ppt salinity from upstream to marine zone and estuaries. So our hypothesis is as salinity increase, we expect electrical double layer compressed and critical shear stress and yield stress decrease. So in our first study, we studied the effect of salt on critical shear stress, and we recently published this paper in Water Resource Research Journal. It's published a couple months ago. So in this study, we prepared the cohesive sediment mixture with salinity ranging from 0 to 35 ppt, and we conduct flume experiments, flume tests. Basically, we place the sample in the middle of the flume and increase the shear stress incrementally under the fixed protocol. In parallel, also, we did rheological tests to measure the yield stress and flow point stress and viscosity of the materials. Also, we did a very simple but interesting visualization test. So we simply tilted the samples 30 degrees to see the gelatinous state of the material. And as you can see with the fresh water, 0 ppt material hold its shape in the 30 degree. But in 3 and 5 ppt, it's a start flowing and creeping downward, down slope. And above the 10 ppt, it have like fluid-like behavior, and material surface goes horizontal. Flume test results show that erosion start with the pit formation that we expect from cohesive sediments, and after the pit formation, we have a mass erosion. So we have a pit formation prior to the mass erosion, and critical shear stress of the mass erosion drops sharply from 0 to 35 ppt. It's dropped more than 2 orders of magnitude. Results of the rheological test show the same behavior, more or less. We have again sharp drop more than 2 orders of magnitude in both flow point stress and yield stress between 0 to 35 ppt. And the interesting point is, like, it seems that flow point stress follow the mass erosion and yield stress follow the pit formation. And all of these results tell us the same story. So from 0 to 35 ppt salinity, material goes from gel-like to the fluid-like, and critical shear stress and all the rheological properties drop sharply. But we face an interesting question in this study, actually. Our results show that sediment at 35 ppt is fluid-like, right? But why aren't estuaries and ocean beds fluid-like at 35 ppt at nature? So motivated by this question, we decided to explore biology role in the controlling of the critical shear stress in our next study. So now how biology can affect the critical shear stress. So basically, microorganisms attach to the sediment surface, and as a part of their metabolism, they start producing EPS, extracellular polymer substances. And these EPS are very sticky, and it stick the sediment surface together and bond them together. And this different bonding can have different erosion mechanism. And this is a very cool image showing the biological network stick the different sediments grains together and span between them. The green ones are clay, and like there's the fluctuated of the clay down there. So our hypothesis for this experiment is as EPS and biofilm increase, particles stick together, and we expect that critical shear stress and yield stress this time increase. So this time we prepared the cohesive sediment mixture, but this time we fixed the 35 ppd salinity, and we used synthetic EPS ranging from 0 to 2%. And result of visualization tests show that from 0 to 2% EPS, material goes from fluid-like this time to the gel-like, so it goes back to the gel-like, and it's gained its strength again. Again, critical erosion start this time with formation of the ripple, different kind of ripple, like the elastic ripples, and after that we have a mass erosion. And again, flow point stress and yield stress follow the flume stress, critical shear stress, and it's saying see flow point stress follow the mass erosion and yield stress follow the ripple formation. To further study the role of biofilm, we are now working on the natural algal biofilm in our new study. So in this study, we're growing algal biofilm on sediment surface, in particular filamentous cyanobacteria, which can form biofilm on sediments and can have a centimeter to decimeter thick. These biofilms are different from what William talked about. So yeah, they're much thicker than that scale. And the other ongoing study, which not related to the cohesive sediments, and I work on, is impact of logs on microplastic deposition in infiltration via hyperetic exchange. Yeah, you can see some results from this experiment, infiltration pattern under different log position and discharge. And yeah, this is a very cool video, but I will just go forward because of the time. And yes, by part of my award, I can purchase books. I already ordered these 2 books. Unfortunately, I didn't receive them to give you because show you physically. But these are the covers. So the first one is the Rheology Handbook by Dr. Thomas Mesger, and the other one is an Introduction to Hydraulic of Fine Sediment Transport by Dr. Ashish Mehta. And yeah, these are my group mates, and you guys are amazing. Yeah, thank you.
Well, I feel we at SAFL are really fortunate to have legacies like our former director, Professor Rajant, and former director, Professor Silverman, former director Anderson, okay, for their excellent work. And you can see their legacy, their impacts are felt, okay, here for our students. And they have really someone to look up to, okay, and you also, they are doing wonderful work, okay. Well, congratulations to the 4 student award winners, okay, and well, okay, keep up good work, okay, and also, okay, I want to take this opportunity to thank the families and supporters, friends, former colleagues for making these awards possible. Okay. Also, thanks to the wonderful staffs at the lab and also at the college, okay, for working very hard to have these awards. Okay. And well, one last thing, also from one of our staff, Bridget just emailed me, asking me to remind the 4 student award the winners. Okay, don't forget to take one. Okay, no more, no less, 1 flower with you. Okay, so that is an additional award in addition to the big check you are receiving. With that, I'm concluding this award ceremony.